Today we're going through 2.7 mass to mass stoichiometry as a part of Foundations in Chemistry Part 2, looking at the outcome FC3 using stoichiometry to determine the relative amounts of substances consumed and produced in chemical reactions. You will learn how to determine the relative number of moles in a variety of chemical reactions using balanced chemical equations, how to relate the use of mole to the coefficients in a balanced chemical equation and compare this to the mass as measurable quantities, and how to perform stoichiometric calculations to predict the outcomes of chemical reactions using the correct units and significant digits. Mass-to-mass stoichiometry is when we have a known mass in a chemical equation and used to calculate the mass of another substance being produced or consumed. So our steps are exactly the same as 2.6 notes. We write a balanced chemical equation, identify the given and unknown, convert the given quantity to mole, set up a mole ratio, and calculate. Convert the moles of unknown quantity of the unknown to the unknown quantity, and we finish our answer, writing a sentence answer or to the appropriate significant figures and units. Now, when in 2.6, we just started with moles, so we were able to skip number 3 and number 4, but now we're going to have to go through the entire, number 3, number 5, not number 4. We wrote a balanced chemical equation, identified a given unknown. It was already in moles, so we didn't have to do number 3, and we just set up our mole ratio and calculated, and then our answer was already in moles, so we are finished. Now we'll have to go through all 6 steps because we're starting with mass. We need to convert mass to a mole, set up our mole ratio, and then convert back to whatever units we would like. So this question, our first example here, what mass of aluminum oxide must be decomposed to produce 80 grams of oxygen? We start with writing a balanced chemical equation. We have aluminum oxide, Al2O3. It decomposes into aluminum and oxygen. And if we balance these, our oxygens are 3 on one side and 2 on the other side, so we need to make sure we make those the same. We got a 2 and a 3. And now we have 4 aluminums, so now it's balanced. We then need to write our given and unknowns. So we are looking for a mass of aluminum oxide, which we know is in grams, and we have 80 grams of oxygen. Now whenever we have grams, we know we are going to need to find our molar mass, so I like to find that next. Our molar mass of oxygen, we have 2 oxygens. We don't need to take into account the 3 as part of our balanced chemical equation because we'll use that in our mole ratio. We just look at our chemical compound or chemical formula, and again, do not take into account that coefficient. We have O2. So we have 2 oxygens, which is 16. So it equals to 32. We have 32 grams per mole. And aluminum oxide, our aluminum, we have 2 times, look aluminum up on our periodic table, 26.98 plus oxygen, we have 3 at 16. Then we get 2 times 26.98 plus 3 times 16. 101.96. So 101 0.96 grams per mole. There we go. And now that we figured out all that information, we should be good to go. We first need to start with our number in our question, 80 grams of oxygen, and make sure we write our substance that the number corresponds to, because we're going to need to use the mole ratio in order to relate. So to change it from oxygen to aluminum oxide, we need to make sure we know where that, if oxygen's on the top or oxygen's on the bottom of our ratio. So we start with our number from the question, we convert it to moles. We know we need to convert it to moles using molar mass. And we have grams on top, so we're going to need grams of oxygen on the bottom, which means moles of oxygen go on the top. Now that we've done that, converted our substance to moles, we need to use our molar ratio. And our molar ratio, we have moles of oxygen on top. We need to use those coefficients out front and put 3 moles of oxygen on the bottom to get moles of oxygen to cancel off. And then we put 2 moles of aluminum oxide on top, because that's what we're looking for. If we were just looking for what moles of aluminum oxide must be decomposed, we would just stop here, because if we look at our units, they're in moles of aluminum oxide. Now, it's asking what mass of aluminum oxide must be decomposed. We're going to need to use that molar mass in order to convert back. So 101.96 grams of aluminum oxide goes on top, because we need that moles of aluminum oxide on the bottom to get that to cancel off with our molar ratio. And since we have a lot of numbers happening here, often it's really helpful to multiply everything on the top and write the number down, divided by the number on the bottom, so 32 times 3 times 1, which is 96, and then divide the two together, which is equal to 169.9333, repeating. If we take a look, we need 3 significant figures. So that we have 1, 2, 3, and we look at the number right before, which is a 9. That needs to round up to 170. Now if we take a look at that, 170 does not have 3 significant figures. We now have 2. We need to make sure we put a bar over that 170, or we can go 170 with a decimal, either way. And then we need to write our units, grams of aluminum oxide. So either one of those would be right, or you can write it in scientific notation. That's completely fine, but either one would be correct. And our next example here, how many grams of sodium are required to react completely with 75 grams of chlorine using this reaction? It's already given us a balanced chemical reaction. We're going to need to write our knowns and our unknowns. It's asking for how many grams of sodium we are looking for. And we have 75 grams of chlorine. Ooh, 75 grams of chlorine. When we're working with grams, we know we're going to need to find the molar mass. So we look that up. We have sodium. Look that up on our periodic table, which is 22.99. Grams per mole, and chlorine, there's 2 chlorines, times 35.45, which ends up being 70.9 grams per mole. Once we finish that, we start with our number in the question, which is 75 grams of chlorine. And we convert that to moles using our molar mass. We have to put 70.9 grams of chlorine on the bottom because we want that to cancel off, and then moles of chlorine goes on the top. That our grams cancel off. We've converted to moles. Our next step is using the molar ratio. We take a look at our coefficients out front. New moles of chlorine on the top. We have 1 mole of chlorine on the bottom and 2 moles of sodium on the top. And now that we've converted to moles, we need to convert to whatever units we're looking for, and we're looking for grams of sodium. In order to convert from moles to grams, we need to use molar mass. We use that 22.99 grams of sodium over moles of sodium. And then our moles of sodium cancel off. We multiply all that out, so 70 times 1 times 2 times 22.99 divided by 70.9. We end up with 48.6 to 3 significant figures, so 48.6 grams of sodium. There we go. And our next question's a little bit different. If solid sodium chloride is reacted with 5.418 times 10 to the 22 molecules of sulfuric acid, aqueous solutions of hydrochloric acid and sodium sulfate are formed, how many grams of sodium sulfate would be found in solution? First of all, we need to write our balanced chemical equation. We have solid sodium chloride. Sodium chloride is reacted with aqueous sulfuric acid. This is the double replacement reaction. The sodium goes with sulfate. It tells us sodium sulfate, hydrochloric acid, and sodium sulfate are formed. So hydrochloric acid and sodium sulfate are formed. There we go. Then we need to balance this chemical reaction. We have 2 sodiums, we'll need 2 sodiums, and then we have 2 chlorines, we need 2 chlorines, and it looks like it's balanced. We then need to write our knowns and our unknowns. We have 5.418 times 10 to the 22 molecules. And when we have molecules, we know we're going to need to use Avogadro's number. And then our question's asking how many grams of sodium sulfate would be found in solution. How many grams of sodium sulfate? So I might write that down. So molecules, we need to use Avogadro's number just to remember that. And sodium sulfate, since it's looking for grams, whenever we're looking for grams, we need to make sure we find our molar mass. Now we look up our molar mass of sodium is 22.99. So just on my calculator, I'm going to go 2 times 22.99. And we add that to sulfur. We only have 1 sulfur, which is 32.07. And we add that to 4 times 16, which is our oxygen. Gives us a molar mass of 142.05 grams per mole. And if you're looking at how I'm writing this, I am changing colors just because I find it more important to write down. I was given this, my knowns and my unknowns, in one color, so I just remember that those are what I was given from the question. And everything else is information that I'm just coming up with, like Avogadro's number and our molar mass. That's not given in the question, but they're numbers I know I'm going to need to use as part of my calculations. But the actual numbers given in my question are anything in gray in this case. Now that I've written my knowns and unknowns, I'm going to want to start with the number that was given in the question. So I'll start with 5.418 times 10 to the 22 molecules of sulfuric acid. And I know to convert from molecules to moles, we need to use Avogadro's numbers. We use 6.02 times 10 to the 23 molecules of sulfuric acid, H2SO4, all over mole of H2SO4. Once I've done that, I've converted to moles, I need to use my molar ratio. So we only have 1 mole of sulfuric acid. And we're looking for sodium sulfate, which is 1 mole of sodium sulfate. Now that we've converted to moles of sodium sulfate, I need to convert my final answer to grams using that molar mass. 142.05 grams of sodium sulfate or mole of sodium sulfate. And those cancel off. If I multiply all that out, so 5.418 times 10 to the 22 multiplied by 142.05, I get 7.696 times 10 to the 24. If I divide that by 6.02 times 10 to the 23, I end up getting 12.78 grams to 4 significant figures. I need to write 12.78 grams of sodium Na2SO4. There you go. All done.